Okay, so our goal for this session is to explain how a buffer works. You can find reading for this in OpenStax Chemistry, section 14.6. So first, what is a buffer? Choose as many of these as you think are appropriate. So the best answers here are that a buffer is a solution of a weak acid or a base in which some of that acid or base has been neutralized. Or in other words, that we have a mixture of a weak acid and the conjugate base form. The canonical definition of a buffer is also a solution that resists a change in pH. Notably, this is not a device to torture Chem 132 students, though sometimes it might feel like that. Okay, so a buffer is a solution that resists change in pH. It's made from a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. So the point here is that you have a mixture of both the acid form and the base form. The best buffers have a pKa within plus or minus 1 pH unit of the desired pH of your buffer. So the pH that you want your buffer to stay at. And that means that we have a base to acid, or conjugate base to conjugate acid ratio between 0.1, 1 to 10, and 10, 10 to 1. We'll talk more about that in a minute. Buffers are real. One great example of a buffer is the buffering system in your blood. Your body keeps your blood pH tightly controlled between pH 7.35 and 7.45. And it does so by having a mixture of carbonic acid and hydrogen carbonate in your blood. And so that way, whenever an acidic substance is added to your blood, a little bit of the HCO3- can react with the acidic substance. Or if a basic substance is added to your blood, it can react a little bit with the acid form, H2CO3. And in that way, we're just slightly shifting the weak acid, weak base equilibrium according to Le Chatelier principle. So thinking about that in a little bit more detail, if we picture what the molecules are doing, we see that buffers resist a change in pH because added H3O plus or OH minus, strong acid or strong base, only shifts a weak acid equilibrium slightly. So if we start with the picture on the left, we see that when we add the 1, 2, 3, 4, 5, 6 HCl molecules to our unbuffered solution, that produces 1, 2, 3, 4, 5, 6 H3O plus molecules. Okay? If we compare that to our buffered solution over on the right, we see that before we add HCl, we've got 1 H3O plus in our solution. Then we add 6 HCl molecules, and then after the buffer is added, you can see that we still have only 1 H3O plus molecule. So what happened there is that the added HCl molecules reacted with the conjugate base form to shift the weak acid, weak base equilibrium toward the reactants, according to Le Chatelier's principle. So we added a product, and that means that we produced more reactants. And in so doing, that used up most of the added H3O+. So the result is that the pH, which you remember is the negative log of the H3O+ concentration, it doesn't really change. So the pH stays the same, because that added H3O plus has something to react with. This figure from your textbook says the same thing. So you see in the middle, we have equal molar amounts of H3O of the conjugate acid form, acetic acid, and the conjugate base form, acetate. And so when we add a little bit of H3O plus going to the left, we see that we change that H3O plus, we change the acetic acid acetate ratio a little bit. And when we add OH minus, we change the the acetic acid acetate ratio a little bit in the other direction. But the point is that we still have relatively large amounts of both of those present in solution. Okay, so given that we need a mixture of the conjugate acid form and the conjugate base form, which of these solutions could produce a buffer? So the best answers here are B and E. Let's take them one at a time. A is not going to produce a buffer because there we have a mixture of a strong acid and its conjugate base, KNO3. And so that is not going to produce a buffer solution because we don't have a weak acid and its conjugate base. If we look at mixing 0.1 molar NaNO2 and 0.1 molar HNO2, nitrous acid is a weak acid. So we have HNO2. We also have its conjugate base provided by the 0.1 molar NaNO2. Remember that in a salt, the sodium ion there has no effect on the pH of the solution. It's neutral. Okay, C is a mixture of a strong acid and a weak base, but they're in equal amounts. So this is going to form water and NH4Cl. We don't have any of the NH3 form left, so that's not going to be a buffer. So if we look at option D, 0.2 molar HCl and 0.1 molar NH3, in this case, the HCl is going to neutralize all of the NH3 and have some HCl left over, so that'll be an acidic solution as well. And then the one you might not have expected is 0.1 molar NH3 and 0.1 molar HCl and 0.2 molar NH3. So in this reaction, the NH3 can react with the HCl completely to form NH4 plus and Cl minus. Okay, so you see here that NH3 and NH4 plus are a weak base and its conjugate acid. When we have 0.2 molar NH3 and 0.1 molar HCl, we see that the HCl is the limiting reactant. So if all of that reacts, we'll have 0.1 molar NH3 left over, no HCl, and 0.1 molar NH4 plus after the end of the reaction. Okay, so after this reaction occurs, we see that we have a mixture of a weak base and its conjugate acid, and that's how that one can form a buffer solution. So what makes the difference between D and E is that here in D, the strong acid is in excess, and in E, the weak acid is in excess. So that's a really important difference to remember there.